Well, good afternoon. Thank you very much for the invitation, and it's a great pleasure to be in your beautiful country. It's the first time for me. So I've been asked to talk about input factors of reading in beginners and dyslexics across different languages. And I will try to do this by referring to a computational model. So for our translators, it's a computer model, like a simulation model. And in a way, our talks with the one that just preceded me by Hugh Cates will be quite complementary. While he showed the broad lines and the major themes, I will show some of the little nitty-gritty details about how exactly these different processes that he has been talking about will affect the reading and especially the learning to read process. At the beginning of last century, one of the fathers of experimental psychology already recognized that it would be one of the aims of a psychologist's achievement, one of the outstanding achievements in a psychologist's life, to understand and analyze what we do when we read. And he mentioned one interesting aspect, that it's intricate workings of the human mind and the human brain. At the time, we didn't talk about the brain. And this is certainly something that we are interested, even now, 100 years later, we are still trying to understand what precisely we do when we read, and in the context of dyslexia, when we learn to read, and when this learning to read process fails. And we do this nowadays with more sophisticated methodology, experimental methodology, and with theories. And sometimes the theories are so well specified that we can actually implement them in a computer that makes predictions about how we learn to read and what can go wrong. And I will walk through these different input factors in the context of a computational model of learning to read. Let's have a look at the input factors to the reading system from a very broad, superficial perspective. So before children come to the task of learning to read, they do have spoken language. And we know the spoken language network, we know where it is in the brain. You see this here. And this spoken language network is a coupling between spoken information, phonology, and semantics, right? This is what the child has. It's spoken language. It's a rich system that is there prior to reading. And what does reading really do? It just adds like a new pathway, a new interface, a visual orthographic interface to this spoken language system. This is trivial in a way, but it's fundamental. It's fundamental in understanding what reading is. Reading is finding a new pathway, a new interface that is visual orthographic to a very rich and already in place spoken language system. And at this very superficial level, it shows you the three main input factors that have been already been talked about by Hugh Cates. It is spoken language, which is represented over here. It is the novel visual orthographic interface that has to be learned, which is not predetermined, for which we do not have any predetermined genetic capacity to do. And it's the mapping between this novel visual interface and the spoken language system. So at a very broad level, you see there's three main factors that affect learning to read: spoken language, the visual orthographic interface, and the mapping between these two domains. And of course, that very broad view is too superficial to make precise prediction about what can go wrong, and especially to understand inter-individual differences, which is nowadays one of the main issues in dyslexia research, understanding how different deficits that are there at the outset of reading can lead to different profiles, because you all know there's massive heterogeneity, and we want to understand this. And of course, at a very superficial level, it's very difficult to get to that kind of understanding. And this is why we now apply more precise theories about the learning to read process. And this is what we have been done recently in a work that was published in this paper. And we took what is nowadays the most influential theory of reading development, which has been proposed by David Scher in 1995, and it's called the phonological decoding self-teaching hypothesis. It's very simple. It says, at the heart of reading acquisition is phonological decoding. A child learns very few, very basic, elementary grapheme-phoneme correspondences. Decoding allows a child to access words in the phonological lexicon that are there prior to reading. So this process will allow a child to read, to decode a word that the child has heard before but never seen before. For a child who comes to the task of learning to read, all words are pseudo-words. They are novel, but they know them in their spoken form. So phonological decoding allows you to access the phonological form of words, so words you have heard before but never seen before. When you do this, and this is where self-teaching now comes in the theory, every successful decoding of a word that finds a word in the phonological lexicon allows the child to set up an orthographic representation in the orthographic lexicon. And the phonology that is generated through the decoding process is used as a feedback to improve the decoding process, get decoding better and better, make the decoding process more efficient, allowing the child to decode more words. As José Moret said, this is more than democracy. This is leading the child to total autonomy. It's anarchy in a way. The child will be autonomous by using few decoding and will benefit of the richness of spoken language. That's the most influential theory. Many people still think it's the three-stage theory of Uta Frith, but even that one is totally underspecified as it comes to how do we do it. David Scher's theory is not, which made it possible for us to implement that in a computational model, a computer model. And you see how this works. So, prior to the task of learning to read, the child has a phonological lexicon, knows the spoken words, that is in place. And then children learn about letters, basic letters. And once the basic letters are learned, and probably as a process of learning these letters, it will learn how to map these letters onto phonemes, right? And this in a model can be represented simply as a two-layer associative network. There are two layers, letters and phonemes at the output, and it's linear. There's nothing hidden. It's very simple, linear learning. And this actually is done in school through explicit teaching in every language. Now I'm talking about alphabetic systems. Similar things apply to non-alphabetic languages. This is done through explicit teaching and phonics. So a child will learn a few basic grapheme-phoneme correspondences, a rudimentary decoding system, which could be implemented in that kind of a system. Once the child has done that, it will be able to decode words it has never seen before but heard before. So take the word beer, like it's early in the afternoon, I know, but so take the word beer. It has learned the basic correspondences, a few 40 or so, and it will be able to decode the phoneme sequence beer. Maybe not perfect. Now we're talking here about English. Probably if it's English, it's not perfect. There's noise, but somehow it might get close enough to what could be the candidates. Sometimes they call it the cohorts, the candidates in the phonological lexicon. Which could be beer, bear, bin, bar, and so on. So the decoded word comes close enough, and there will be in the phonological lexicon a selection. There will be a winner, the most strongly activated word in the phonological lexicon that maps that input. So assume here the word beer will win over the others, and in Scher's theory, you will set up an orthographic representation for the word beer. And now is where self-teaching comes in, very importantly. Now, these internally generated decoding, the phonology that is internally generated will be used as an internally generated built-in teaching signal to improve the decoding network. This is what I called anarchy. So you no longer need like an external teacher, like in all other connectionist models, if you're interested in those, where you always have an external supervisor that throughout learning tells you this is correct, this is wrong, this is correct, this is wrong. Not in Scher's theory. Scher's theory is a few associations. You learn decoding, you decode words, you find a word in the phonological lexicon, and the so found phonological form will be used as an internally generated built-in teacher to improve the decoding network itself. Decoding will become more and more efficient, and the child will be able to decode more and more words in an efficient manner. So the child will be autonomous, and that's fundamentally what reading, like learning to read in alphabetic languages, is about. Orthographic development is fundamentally tied to the ability to get this phonological decoding self-teaching loop to work. So the first thing you might want to know is, well, does this work? Sounds like a great idea, but take a language like English, it's horribly inconsistent and irregular. Would that ever be work like for a language like English? And given that this we have implemented as a computer model, we can test this. So we trained a network on 45 basic grapheme correspondences, explicit teaching, like in the school. And then we stopped the explicit teaching and we presented 30,000 words to the model and let it run through the self-teaching decoding process. Exactly the loop I described. You find a word in the phonological lexicon, it wins, you set up an orthographic representation, the phonology is used to improve the decoding network. And even in a language like English, such a model is able to learn and to pronounce correctly 80% of the words rather quickly. This is English. 80% is not bad for a model that has no hidden processes, just linear learning and based. It starts small, 45 correspondences, and scales up to these 30,000 words. The other 20% in English, they have to be learned by other means. They are irregular, inconsistent, hopefully so. So words like yacht, the boat on the lake. So these words have to be learned by other means, and they will be learned by other means. In languages that are more transparent, German, Italian, Finnish, maybe even, certainly even Portuguese, this rate will be much higher. The words you can learn through decoding will be much, much higher. And you see very quickly, this is what happens in the phonological lexicon, very quickly in the learning process. The correct word in this cohort of words is also the most active one. The most active word in the phonological lexicon that it gets activated through the decoding process is the correct one. So that shows you it's a very efficient process. So now we have shown that learning loop works. We can go back and see what are the input factors, that was the title of my talk, that will affect the learning loop. Well, the first one is obvious, it's letters, right? Any deficits and problems in the processing of letters will impair, at the first input level, the entire process, not just like a subpart, because we're talking about learning, and dyslexia is a learning disorder. It's not at the end state of some system that has developed and crashes. It is the learning process that is not working well. So what can affect letter processing? There's visual deficits, and John Stein knows about those, and he can comment on those. Every kind of visual, but typically we handle those quite well, like low visual acuity, for example, that's detected early and that is fixed rapidly. But there are more subtle problems with regard to this letter processing. One is the coding of letter positions. That is something very specific to reading. So you have to have the identity of letters, but also the position of letters. And that is something that is very specific to reading. Illiterates, for example, they are blind to changes of letter order. You present two words, and they have to say, are they the same, are they different? And if you change the internal letters of a word, casino, you make it caniso, you change the internal letters, illiterates are blind. They will not be able to say, well, this is the same word, because letter decoding develops through, letter position decoding develops through reading. But there might also be independent letter position decoding deficits, because these have been reported recently in the literature, not a big amount of children with dyslexia, but like some of them that have apparently specific deficits in letter position coding, and they are now called letter position coding dyslexia. And another one that has been discussed, another factor that affects that letter processing stage that has been discussed quite a lot in the literature is visual attention deficits, or visual, sometimes it's called visual span. And in fact, although it's called visual attention, the tasks that are typically used by the authors are basically detection of consonants in consonant strings and our ability to process in parallel several letters, groups of letters, bigger chunks of letters, so that we can efficiently enter that decoding network, right? So these visual span deficits are very tightly linked to the quality of that letter processing input. So these are a few things that can affect letter processing. Given that we have a model, we can look, what would that learning process look like if you had such a deficit at the outset of reading, at the start of reading? This is what you can do in a model. You can't do in people, because you get them when they are dyslexics. It's very hard to go back, and longitudinal studies are rare. But in a model, you can do that very easily. So here we simulate sort of a visual span or letter coding deficit. So each letter in a word was switched with a letter next to it with a certain probability. So you present, for example, the word cat, and with a certain probability, you swap some of the letters. Now here it might be act, so the child will visually perceive act. It will decode act. It will find act in the phonological lexicon. Act might win. You set up an orthographic representation for the visually seen word cat corresponding to act. Act will be used as a teaching signal, so the wrong phonology for the orthographic form cat. So things are messed up. But they are messed up not only visually, that's what I want you to tell, but they are messed up because the phonological decoding network through that visual error will get a wrong teaching signal. It will learn wrong correspondences. What will happen? So in red, sorry, let's go back. In red, you have the normal reading performance, and then as you go down, you see when this happens, this visual deficit happens 2% of the time, so not very often. It doesn't matter so much. But when this happens more, like 4%, 6%, 8%, 10%, when it happens on 10% of the occasion that internal letters swap on one particular decoding event, orthographic learning will be impaired in the model by about 20%. So it will make the learning to read process a lot harder. But it makes it harder through the regular, phonological decoding loop. It's not independent. It's not like an independent deficit that is stuck on somewhere. So one factor that is known that affects the processing quality at the letter level is crowding. So that has been discussed also by you, Kate, before. Crowding is a phenomena where objects that are surrounded by other objects are masked, lateral masking. So you see that quite nicely here. You fixate the dot in the middle, and without moving your eyes, don't cheat, you will see that the letter R to the right is perfectly visible, and the R to the left is not visible. It's masked by surrounding letters. This is a perceptual phenomena that everybody has. But through reading experience, our visual system gets a handle on this, probably because we need to process several letters in groups of letters, and so, we solve this problem. But dyslexics, might not solve that problem for two reasons. A, they don't read enough, or B, they might have, a small group of dyslexics might have fundamental problems with that kind of crowding. One efficient way to get rid of crowding is spacing. So again, fixate the point in the middle, and you see that the C to the right becomes visible, and the C to the left is still masked, although the distances are perfectly identical, The distances on the retina are the same, just the crowding is different. And we have tested this, so by improving spacing, you reduce crowding, and you show that, in fact, learning, it's not learning to read, but it's just reading is easier. So you have normally spaced text, you have more spaced text where the letters in a word are pulled apart, the words are pulled apart, and the lines. The effect comes from spacing the letters in a word, and you see that children with dyslexia, it's a group of 30 Italian dyslexics and 40 French dyslexics, they benefit from spacing. This is normal, this is spaced text. They benefit from spacing, they commit less errors, and they read faster. So that's one of the factors where you see that a deficit at one of the input levels, at the letter level, can produce effects that are detrimental for learning, and you can actually intervene in a way. It's an aid, it's not an intervention, nothing functionally changes, but for some of the kids who have these effects, you can actually do something. And we have proposed like an application that is downloadable on the iPhone, on tablets, where you can actually check whether your spacing is optimal for you, so children can pick a spacing and then they get sentences to read and they can see whether it helps them, because our claim is that not all children will have these input at the letter level deficits. So it's important to know who has it and whether it actually helps. And again, in this perspective of having a computational model, it's interesting because one of the factors that you pointed out, you want to be able to predict when deficits are there at the outset, what would their reading be like? And with a computational model like ours, we can actually do that. We can simulate different subtypes, but this will be beyond the scope of the talk today. So let's look at the other main domain. It's phonemes. And I mean, you have heard about this, so I don't need to go much into details. It's the most well-documented input factor to the network that can cause problems. So there's poor phoneme discrimination when a child cannot discriminate for some consonants that are voiced, the B and the P, for example. It doesn't matter so much in spoken language because you have a lot of context. So whether it's ball or Paul, if you know that they're talking about soccer, you know it's ball. And so it's very difficult even to detect these subtle speech discrimination problems. However, in reading, it becomes fundamentally important because the teacher in the class in a noisy condition will say, this is the letter B and it corresponds to B. Learn it. And this is this explicit teaching that I was talking about. This very small correspondence is true in any language, no matter the orthographic complexity. If the teacher says this is the letter B and it corresponds to B, and the child sometimes hears it's P or it's B, it will be catastrophic for the learning to read process, no matter how much you have to learn. Even a child in Finland who has to learn only 20 of them will suffer from that. So that's one of the problems. There might be speech perception deficits that can, particularly salient in noisy conditions, but classrooms tend to be noisy. And then, of course, there's phonological awareness, and it's the main predictor of reading. It's the similar idea. If you're not able to isolate phonemes, when a teacher says this is the letter B, it corresponds to B, and you don't actually grasp what the phoneme is, and you don't have it in your system, it will make it more difficult. But phoneme awareness, is that more interactive process where it comes a bit through reading and it's there prior. So anyway, having a model, again, we can see what happens to the learning to read process if you simulate a phoneme deficit. So here we switch a phoneme at that level with a phonetically similar phoneme, say B against P on a certain number of occasions. Again, you get beer. The decoding network typically would decode beer, but now it's peer on a certain number of occasions. The B is swapped against the P. A wrong word will eventually win, which is peer. And again, there's a wrong connection that is set up between the beer and the peer. The network is trained with a wrong teaching signal, peer phonology for a beer stimuli. The whole decoding process is impaired by a subtle deficit. And when that happens on, say, 15, on here, it's 5% of the trials, it doesn't matter so much. So very subtle impairments, 5%, you get over it. But when this happens at 15%, 25%, 35%, and now here it's half of the time. When it happens at 50% of the times, there is no orthographic learning anymore. There is none. And this would be true, again, in any language. No matter how the complexities, or the Finnish, they are better off because they have only 20 of these correspondents to learn, whilst the Portuguese will have to learn many more. But they're not better off in terms of getting that decoding system to work. Another factor that is in the model, I won't talk a whole lot about it, but I just want to mention it's there, but you, Kate's mentioned it's important. It's important for this theoretical reason, but that you need to go to the phonological lexicon to find a candidate. So poor vocabulary, for example, is definitely a problem in the model because you can decode fine. So you can decode fine the beer in your decoding network because you need only these few associations. But if you don't have the word in your phonological lexicon, then you don't find an entry. So the child will think, well, might not even a word, right? So, and it's detrimental for comprehension because comprehension is amodal, and if you don't comprehend the word beer in spoken language, well, you can't get it from written. But it's less important than the other factors for a simple reason, that even if you don't have the word in the phonological lexicon, decoding will get you a word in the phonological lexicon, because many words we learn them through reading. So even with a poor vocabulary, it's not as detrimental as poor phoneme processes, because once you get the basic decoding to work, you set up these phonological representations in the phonological lexicon through reading. So just theoretically speaking, and the data actually shows this, and I come to this in a second, poor vocabulary is not as damaging as poor phoneme processing for this very, very simple reason. The other factor, of course, is that has been discussed in the literature, but it's a vague concept. It's the quality of lexical representations. You can imagine they're more noisy in a way, whatever that means. And of course, we haven't simulated this, but it's very easy to do. If you have like noisy representation, there will be maybe more candidates in the phonological lexicon, harder to select, and so on. And you could see that it would be, it's quite easy to see why that would be detrimental. So let's just for the moment have a look at these three domains: letters, phonemes, and phonological lexicon. And I should actually say, phonological lexicon, we always think of it, the quality of the phonological lexicon, but the other factor, of course, is the access to the phonological lexicon, and that is measured in tasks that are highly predictive of reading, like rapid automized naming or just object naming. Very simple tasks that can be done prior to reading, pre-reading, because everybody can name objects, and it reflects exactly this process. how quickly you access the phonological lexicon. And in contrast to vocabulary, rapid naming, rapidly accessing the phonological lexicon is a main predictor of failure and success in learning to read. So let's just have a quick empirical look at how important these different levels are. What I present you here with the dots are actually children. The green ones are the control children, and the white ones are the dyslexics. Every point is a child. The scores are Z scores, so everybody is on the same scale, centered around of the control. So you can look at the white ones as compared to the controls. And you see, like in a basic attention task here, it's sustained attention, but we have similar results for visual spatial attention. You can look at how big is the deficit and how many children are affected, because this is what we want to know in terms of what's the heterogeneity and what is the importance of that input factor. Well, I say how important it is. Keep in mind, this is not longitudinal. This is not at the outset of reading. This is already in the reading process. But it gives you an idea how important these factors are. So in a basic attention task, out of these 24 children, you have 3 that are 1 standard deviation below the means of the controls. So a few kids have these attention problems, and you can see how it might affect letter processing through visual spatial attention, as I showed you, like the crowding paradigm. Let's look at letter processing. So here it was a basic, very basic task. It was letters detection in consonant strings. No phonology. So it's consonants, non-pronounceable consonant strings, and you had to simply detect the letter in a string of letters. And for those who know the literature, this is exactly the task that is used by people arguing for the visual attention span deficit. It's basic letter processing in consonant strings. And you see there's something about that. So about half of the kids are 1 standard deviation below the means. So the size of the deficit has increased. So you find kids that are -3 standard deviation below the mean. So there's something about letter processing. Here we can't say whether it's at the outset of reading, because they're already in the reading, whether it's a consequence, but it's something to be taken seriously when you get children even 3 years later. Here's our phoneme deficit, classic picture. Now it's almost 3/4 of the children have deficits. The deficits have increased in size to -7 standard deviations, a massive deficit in a basic phoneme discrimination task. Of course, these are all the same children. And this is object naming, rapidly naming objects, so it's representing access to the phonological lexicon. Here that task doesn't rely on reading, so it's a good predictor in how quickly you can access the phonological lexicon. About 2/3 have deficits. So it's interesting to look at these kind of data, because it shows you how many children are affected, how important are these different input factors. And you see like a general pattern that has been already mentioned a couple of times. Phonological deficits outweigh the visual attentional deficits in number of children affected and the size of the deficit that is found. That is one thing. And you see there's heterogeneity, and this is not the topic of my talk, but we have analyzed these children in the model and simulated their performance child by child, and there's various combinations of deficits that are unpredicted by all current theory. So like a dual root theory that says there's these visual problems, orthographic, the lexical, and the phonological, they will predict like clear-cut differences. There are none. So you find every kind of combination of deficits, but if we feed the model these deficits, it will predict their reading outcome on like irregular words, non-words, and so on. But I don't have the time to talk about this, but this is already published. Here's just, because we're interested in cross-language differences, a study of ours where we looked at the predictors of reading failure and success in 5 languages: Finland, Hungary, Netherlands, Portugal. This is why I chose it, because it has some Portuguese data, and France. And you see, what has already been referred to a lot. Phonological awareness here in every language is the main predictor. This is a regression model, simultaneous, where all these variables are entered simultaneously. You see it's the main factor in all languages predicting reading failure and success, followed by rapid automized naming, so it's accessing the phonological lexicon in the model. And vocabulary, you see, has a minor influence. It was only in one language and a little bit in French. So it's more, sort of a little bit more, it's weaker and a bit more random in a way. I mean, you can tell stories about why the Finnish vocabulary is important because decoding is so easy, and when decoding is easy, what's left is whether you know the word or not, but then this is also not so consistent with other reports. Anyway, it's not the topic. This is data that you has already mentioned. It's from a beautiful longitudinal study by Heikki Luutinen. It's the eVascular longitudinal project where they had the unique opportunity to follow up children from birth. Right, so that is prior to reading. So now we're talking business here about what are the factors that predict reading outcome prior to reading. So the 1, 2, 3, 5, this is ages when they measured these different skills. And you see they have like these main skills that we are interested in. This is your spoken language, expressive speech, that is like late talking, what you has referred to. The phonological skills, which is like the classic, like, you know, phonological awareness, rhyme, syllable counting, and so on. You have letter knowledge, memory, and rapid naming. And it's a complicated picture, I know, I apologize, but you're interested in these two colored groups, the blue one and the green one. These kids end up being dyslexic readers by the age of 7, right? This is these two groups, and they are compared with the black line, which is the kids that do not end up with dyslexia after 7 years. And again, you know, I want to make this really short, but again, you see the main patterns. Spoken language skills. There are subtle deficits. For example, in expressive speech, at the age of 5 or at the age of 3, you do see, you know, about minus 0.5, like half a standard deviation deficit, subtle deficits in speech production. In receptive speech at the age of 5, you see subtle differences. So spoken language is a factor. It's not huge. The effect sizes are not huge, but they are there. Compare that to the phonological skills. So in my model, that's the phoneme level. That's our ability to, by the end of 5, so it's difficult about here, 5 to 6, you want to have the phonemes in the phoneme system as clear as possible, because decoding is, if not, decoding doesn't work. That's what I've shown you in the simulation. Decoding will fail, and that's a key predictor here longitudinally for these two groups who end up being dyslexia. And the other factor is letter knowledge. Early on they might be different, like different profiles, different subtypes, but you see at the age of 5, both groups have deficits in letter knowledge prior to reading, which tend to be predictors of the reading outcome. So this is interesting. It confirms like this in a nutshell, that these 3 factors, and these are exactly the ones that are important for the learning loop, how they, even prior to reading, can be impaired for some children. And again, there are differences. And these differences we want to understand, and that's one of the challenges we're facing nowadays. One other factor I want to talk about because it's important. So now we've looked at letter processing, phoneme processing, phonological lexicon. But then there is the mapping between the two. So it's the mapping between the letters and the phonemes. And that's an interesting process in its own right. So it's that, what initially that explicit teaching process for 45 in English, grapheme, phoneme correspondences, and so on. And there can be difficulties on deficits in terms of teaching methods. That's an issue often ignored, but of course, wrong teaching methods that will not teach you efficiently the grapheme phoneme correspondences you need in order to become a good decoder, an autonomous decoder, will lead to failure. And José mentioned that this morning. There is cross-language differences related to transparency. I'll talk about this. And then there's learning rate. Learning rate is interesting because that's how good are you at learning a cross-modal mapping between a world of symbols, of vision, and a world of sounds. There's a lot of brain imaging data now, and you, Kate's in the talk just before, mentioned you could even have a paradigm that measures learning rate. That could be this dynamic learning, where you present symbols and they have to teach novel. This tells you something about learning rate independent of the letter level and the phoneme level. So in terms of, see, what I'm trying to do is tell you what are the necessary subcomponents of that model and how can we assess them and then simulate the outcomes even prior to reading. So let's have a quick look at transparency. So that's an interesting issue and how that influences then teaching methods. So you know in languages differ in how consistently, regularly they convert letters into sounds. Finnish has no inconsistency. They have 20 letters and there's 20 phonemes. The problem is solved in, that explicit teaching is solved in a few weeks. The rest of the time they spend decoding and automatizing. They have other problems, because it always comes as a price. So you have easy decoding and then you pay the price in complex morphology, for example. But at least at the decoding level, and that's important to get into the reading process, they are better off, and you see there's no inconsistency. Then you have Hungarian. That index uses just the first letter in a large corpus. There's some inconsistency. Dutch, some more. Portuguese, see, there is more inconsistency than in others, and that makes sense because you have, 22 consonants, you have now 9 oral vowels, and you have, I don't know how many nasal vowels, and you only have 26 letters. And of course, this produces, you have a rich phoneme repertoire, and you have a limited number of letters. This produces inconsistency, and you have genuine inconsistency, the O being different in taco and boca and bonito. This is like generous inconsistency that makes it harder. French is up here, and English is a comparison for those who are interested, is up in the sky. I always like this. Anyway, so consistency. Now, in this model, where everything is about mapping letters onto phonemes initially, consistency should be the main factor in how quickly children acquire a language. And this is exactly what Seymour has shown in this it's an old slide, in this first European study, where you see the languages are ordered nicely. This is reading performance in terms of accuracy after the first year of reading. Finnish and German are almost at ceiling. Here is Dutch. Here is Portuguese, Danish, and English up there. English, after the first year of schooling, is only 30% of words. And in terms of the time, reading times, this is syllables per second. So reading speed, again, Finnish and German up there, Dutch, Portuguese, Portuguese, French, and English. It follows precisely the consistency of the language. And that should be the case if phonological decoding is at the heart of reading acquisition. Say, if there were other means, English and German, for example, they have almost identical orthography. They differ in the mapping, but the orthography is similar. If they could learn it visually, they would learn it visually. They have a good memory system, and there wouldn't be cross-language differences. But there are cross-language differences because fundamentally reading is about getting this learning loop to work, and the learning loop is about phonological decoding. So just quickly, as we stated in the psycholinguistic grain size theory, teaching. So learning is fundamentally finding optimal grain sizes that map the world of orthography onto phonology, and that depends on the orthographic depth. And the more inconsistent the language, the larger you need to learn larger units, because the larger the unit, the more consistent the unit. So in English, it helps you to learn rhymes and syllable and so on. And teaching needs to emphasize those units. So again, Italian and Finnish, it's easy. By Christmas, they learn to read. They have 20 letters and they're done. In French, Portuguese, The problem is not that they will use different strategies and procedures, but there is more to learn, because they have to learn not only in French, for example, that O is O and U is U, but they have to learn that two letters together are a different phoneme. O-U together is U, so it's a different phoneme. In Portuguese, you have to learn context-dependent variables. And context-dependent means larger chunks. You need to learn that a letter that is surrounded by others gets a different pronunciation. There is simply more to learn, and that takes longer. It's nothing else. And it's respectable. You cannot expect children to learn to be good decoders by Christmas like the Italians, but because you have to learn more things. And in English, it's even hopeless, because the letters and the graphemes are inconsistent. And good teaching need to find compromises at these grain size levels, because you need to teach letters and graphemes, but not alone, because you can't get so far. So you need to help you with different grain size, like rhymes and syllables. And at the level I showed you, 20% of the words, they have to be learned at the whole word level. But what does it mean? We're learning a word at the whole word level. It still means that you learn the mapping between orthography and phonology at the largest grain size. So fundamentally, the process is the same. There is no different kinds of strategies that will be weighted differently with different learning routines and so on. So I'm almost done, but I started late. I hope you have counted this. What do we know about orthographic development? So that's one of the challenges, because sort of an area that is not well understood, and that's something we need to understand better. So in Scher's theory, it's easy, but it's sort of a bit underspecified in our model as well. So it simply says, when you find a word in the phonological lexicon, you set up an orthographic representation. And Scher has shown that that seems to be extremely fast, robust, and long-lasting, provided that you go through the phonological decoding process. So this is the kind of data that he presented. So he had children read passages, text passages, and then there were novel words that children could decode. So they would decode a novel word, and it would fit in some sort of semantic category. And even if they were presented with that word only 2 times, you see after 3 times, they read this passage, they don't know what the task is about. They just read this sentence passage, and 3 days later, you get an orthographic choice task where you have 2 homophones, words that sound alike. And then they get asked, what's the right spelling of that word? And after 3 days, with only 2 exposures, they have it, 75%, and it lasts. Even after 30 days, you get asked after 30 days, they still know the right orthography. This process is poorly understood, and there might be deficits in dyslexia to do with that setting up of orthographic representation. And that's different from accessing these representations. But there's something that could be going wrong that we still need to understand in dyslexia. Very importantly, and he has shown this, mere visual exposure to these words doesn't do the job. If you don't go through the phonological learning loop, there is no orthographic learning. Just presenting them visually doesn't work. And just almost anecdotal, this is one of the studies that we have done in our animal lab. So we have like these nice little baboons, and we taught them to do a lexical decision task. We taught them visual words, to discriminate words from non-words. And one thing that is interesting in that study, it's not that they are able to do it, but see how long it takes them to actually do it. So our best monkey, it's Dan, not Stan. Sometimes they say Stan. Anyway, was able to learn 308 words in a month. It's not bad. It's good enough for science. But look at the number of trials that are reinforced. Every trial has an external teacher, where it says it's wrong, it's right, you get the food, you don't get the food, and so on. It takes them about 20,000 encounters. That's fundamentally different to the kind of data that Scher presented. So orthographic learning is possible, bottom-up learning. So learning statistical regularities by a visual system that is fairly similar to ours is possible. The monkey learns orthographic regularities and so on at a certain level, but it takes a lot of reinforced trials in order to do that. That's fundamentally different from what children are able to do through phonological decoding in setting up these orthographic representation. But there might be a process in terms of accessing these orthographic representation that relies on similar processes, but these are long. These are implicit, and they are long to emerge, getting sensitive to this orthographic type of access that is independent of phonology. So if it exists, I would assume, based on this kind of data, it takes long to emerge. Anyway, so here are then my conclusions. So I tried to show you that learning to read is fundamentally based on phonological decoding, and that is true in every alphabetic language. Phonological decoding is most strongly affected by poor phoneme discrimination. You can use phonology awareness as a proxy, but again, that's affected also by letter processing. Poor letter processing and poor access to the phonological lexicon. So here the take-home message is phonological decoding. Often it's seen as a poorly phonological skill, but it also relies on good letter processing, as an example. So you have to take that as a whole if you want to understand a developmental disorder. And then, of course, poor access to the phonological lexicon, because if you decode but you don't access the phonological lexicon, you can't learn either. Orthographic transparency affects the learning rate and the choice of teaching method. So the ease with which we can teach is certainly affected by orthographic transparency and how quickly you learn it. It's not the deficit. So as I said, the Finnish or the Germans, they will have the same kind of problems. So even if you have to learn only 20 associations, when the phonemes are not good, you will be in trouble. And that's what the data shows. However, there's one fundamental difference. And that's important to sort of recognize, is what, it's actually a comment made to me by Paulezo, like one of the fathers of these cross-language studies. It's the give-up threshold. So when you have to learn more units, that would be the case in Portuguese or in English, it's not the fundamental deficits, but it's the give-up threshold. It becomes so tedious and so difficult to do that. So 20, you might get away with it. But if it's hundreds of correspondences, then at some point children might give up and say, like, I don't do that decoding anymore. That's just, I won't get it. I'll do something else. And something else is like our baboons. So it will take a month to learn 300 words. And that is not a good option. So good teaching and good intervention needs to focus that all the prerequisites that are needed to get this decoding self-teaching loop working are in place and are reinforced at the appropriate time window, developmental time window. Attention can be very helpful, but do it at the right time window. Playing computer games with action games is not a good idea by the age of 10 because the system will need other kind of input. It might be helpful at the age of 5 where you will get ready to focus your spatial attention on positions and sort of control crowding and so on. It has to be at the right developmental time window. And as I've shown you some of it, we can simulate developmental trajectories of reading outcome for individual children, and we have done that now on a big database by Dick Olson, where he shows how children end up at different profiles, bad at irregular words and non-words and so on, and he has like underlying measures that we use in the model that we inject in the model and see that, and we can actually predict and see that the model predicts which children will read, for example, irregular words more poorly and so on. But anyway, I didn't have the time to talk about it. And having such a model is important for early detection and intervention of at-risk children, because you can sort of, if you have appropriate tasks, and this is what of course you need prior to reading, you can see, with that kind of a size of a deficit, a visual deficit, for example, what is the likely outcome? And we're getting quite close. In terms of the Olson data, we're about 80% of good prediction only on the basis of the input factors that we have, and that's not even developmentally. So there's a good chance of improving on that. So thanks a lot for your attention, and sorry for going over time. Okay, there's 2 questions, I heard. Yeah? Ah. Okay. Oh, that will be in Portuguese. You have a question? Oh.
Posso falar? Professor Ziegler, eu sou João Luiz Antunes, sou coordenador do Instituto Alfa e Beto na região sul do país. Aproveitando para a gente transferir para a nossa realidade de escola, num idioma como o português, considerado regular, como poderíamos fazer para melhorar fatores de input linguísticos para que as crianças disléxicas adquiram melhor qualidade de aprendizagem e maximizem seu desempenho cognitivo?
Yeah, so I repeat the question. I mean, what can you do in a regular language like Portuguese to maximize the reading outcome and work on the linguistic input in order to do this? I mean, as I said, first of all, Portuguese is not regular, as I shown in the statistics. So that has to be taken into account. And you have to be realistic about it. It won't be as easy as Italian and Finnish no matter what you do. But once you recognize this, you have to highlight and do innovative pedagogy in order to show you need the letters, and you will get them quite easily, but you need a lot of context. And so use an intelligently done teaching curricula where you progressively introduce using factors like consistency, frequency, the kind of context, group sessions where you don't produce catastrophic interference, where you don't teach things that are immediately inconsistent, and so on. And the other factors, prior to reading in all languages, phonological awareness. So this is it's a factor that can be trained very easily, and probably is done. If it's not done, the transition between the end of like maternal school or kindergarten or however you call it and the first grade is crucial in these skills. I don't know if that's done enough in Portuguese, but it should be embedded in the teaching curricula in terms of getting them ready, having these skills ready. They don't have to be taught at the age of 4, there's no, or 5, but you can take your time, and the Finnish example shows that. But at some point, be systematic about what you do. So they need the letters, properly. They need capacities like letters in string detection, and they need good phoneme awareness and phoneme discrimination by the very traditional methods. And then, as I said, in terms of the decoding, I think systematicity is the most important thing. I mean, the English managed, and so I mean, in England they have done it now quite nicely with a curriculum that tries to respect these things. And there's not so many linguistic variables. I mean, once you have the frequency of words, you have the consistency of the correspondence, you have some factors like complexity, some consonant clusters are more difficult, syllabification maybe, and so.
I wonder if you could tell us about the reading process of the profoundly deaf people.
Yeah, I'm not so much an expert in profoundly deaf reading, but certainly they are reading impaired. So it is a tremendous handicap of not having a phonological. But then it's a complex area because they use a lot of like the motor sort of the articulatory skills that are close to phonology as a substitute to get some systematicity. Then some of them are implanted with cochlear implants and certainly the profoundly deaf. I mean, if you look at it, they will read like dyslexics in very similarly. There's maybe a few cases, but you will find a good explanation. So the ones who are perfectly good readers, profoundly deaf, there are explanations in terms of the codes they use, and as I say, I'm not radical about these things. If you have very good, substitution skills, you might get away with it. But again, I mean, there might be some extraordinary children who can visually memorize. I mean, Rainman, the autist. I mean, he could memorize telephone numbers, a telephone annuary. I mean, there are children who have extraordinary skills, but the normal child cannot do that. And the reason is very simple, as David Scher pointed out quite beautifully. If you don't have phonology, something that gets you the order and abstracts away that information, learning words visually is like memorizing telephone numbers, where you have the right letters, the right numbers in the right order. And think about it. If you have to memorize words as if they were telephone numbers, you don't have any other aid. And phonology is so beautiful because it is something that comes from language acquisition. It's for free. We have it. We don't have to learn it. Everybody has it, apart from profoundly deaf. But again, they use other means. And it helps you because the letters, transcribe this phonology. It helps you to get that sequence for free. So, okay, thank you very much.
Agradecemos as palavras do Dr. Johannes Ziegler.